Welcome back to Inorganic Tutors Institute. In today's lecture, we are going to dive deep into the concept of quotient rings. We are going to make it very practical for everybody to get the concept behind quotient rings. Okay, before we get started, we have to look at what rings are, because you can sense the word rings in the main topic, quotient rings, right? So we have to look at what rings are. We have to look at what sub rings are. Then we talk about ideals and coset before we move on to the quotient rings itself. Okay, so first of all, we start with rings. Okay, so from the abstract one, we know that rings are defined based on two binary operations. Okay, so a ring is a set. A ring is a set R. A ring is a set R. So note that a ring is a set R. Okay, and this set R is equipped with two binary operations. So equipped with two binary operations. Okay, so with these two binary operations, they are addition and multiplication. So rings are defined under two operations, under addition and under multiplication. So that is the definition for rings. Okay, and under the addition, it is a group, right? It is an abelian group, right? Under the addition, it is an abelian group, right? And you know that in the abelian group, you can talk about commutativity, you can talk about associativity. It has an additive inverse and also an identity 0, right? So you have to know that under the addition, you have is an abelian group, and within that you can talk about commutativity. You can talk about associativity. You can talk about additive identity, right? Additive identity, which is 0. Okay, and you can talk about additive inverse. Okay, so that is for rings defined under addition. These are what it entails. It's an abelian group of which it's commutative, associative, additive identity 0, and additive inverse. Okay, let's look at the rings under the multiplication, right? You know that under the multiplication it is a semi-group, okay? And in this case, it is just associative under multiplication. So under this, you can talk about associative multiplication. Associative multiplication. So that is a semi-group, semi-abelian group. Semi-abelian group. So under the multiplication is a semi-abelian group. And in that, you can talk about associative multiplication. So don't forget this definition for rings. Under rings, when you talk about rings, they are defined or they are equipped with two binary operations, addition and multiplication. And rings under addition is an abelian group. And you know that in the abelian group, you can talk about commutativity, you can talk about associativity, and you can talk about additive identity, which is 0 and the additive inverse. Then you look at the under the multiplication is a semigroup. Okay, so the last axiom is the distributive law, right? So the last thing is, so let's call that the number 3, which is the distributive laws holds, right? So in the distributive laws, you can have A of B plus C, and that you have AB plus AC, right? B, you can have A plus B or C equals AC plus BC, right? So that is the distributive law under the rings. Okay, so now you know the axioms that is under that has to satisfy the rings, right? Before you can talk about rings. These are what you have to know, right? So now you know all this. Let's look at some few examples for rings. So examples of rings. So one, you can talk about integers, right? So which is the z. So the z is basically integers under addition and multiplication. So that is integers under addition and multiplication. Integers under addition and multiplication. 2, you can have the standard number system. The standard number system. So that is where you can think of the QRC. The QRC, where the Q represent the rational numbers, the R represent the real numbers, and the C represents the complex numbers. So the standard number systems. So we have the Q, R, and C, right? Where our C where our Q is the rational numbers. Rational numbers. Our R is the real numbers. And the C is the complex numbers. The C is the complex numbers. Okay, so that is the second example for rings. I know you can give more examples of a ring. Okay, so let me give you the last example or the third. Z of x is basically rings of polynomial is basically rings of polynomial with integer coefficients, rings of polynomial with integer coefficients. Okay, so that is the third example that I have been able to give under the rings. Okay, so let me give the fourth example, which is Zn, right? The Zn is integer modulo n. The Zn is integer modulo n. So that is integer modulo n. That is the Zn. All right. So if you are asked to give examples of a ring, you can talk about Z, which is integers under addition and multiplication. 2, you can give the standard number system, which is the QRS, where the Q represents rational numbers, the R represents real numbers, and the C represents the complex numbers. You can also talk about the Z of X, okay? Rings of polynomial with integer coefficients. And also you can talk about the Zn, and that is integer modulo n. Wow, that is amazing, right? So now you know about rings. Let's go ahead and talk about sub-rings. Okay, know about rings, so we can use that as a ladder to climb towards sub-rings, right? So we have to know what a sub-ring is, because we have already know rings. So knowing sub-rings will be much easier, right? Because sub-ring is embedded in rings itself, right? So a sub-ring is a subset. Okay, so it's a subset. It's a subset of the ring, right? It's a subset of the ring, and it's a subset. It becomes a subring. It becomes a subring if one, if one S is closed under subtraction and multiplication. So one, if S is closed under subtraction and multiplication. Two, we've known the first condition. We can talk about subring if S is closed under subtraction and multiplication. 2, if S contains 0, right? Don't forget that in the rings, we have under the ring under addition, we have additive identity, of which it is 0, right? So we are referring it to this subring as well. So S contains, it must contain 0, okay? It must contain 0, and it must behave like, or it behaves like, are you getting the point? It behaves like a ring under the inherited operations. So it contains 0, okay? And it behaves like the ring under the inherited operations. All right, so These are few things you have to know about the sub-ring, because basically if you know about the rings, then knowing about the sub-ring shouldn't be a problem. Okay, so that is what you have to know about the sub-ring. Okay, so now we can look at some few examples of a sub-ring, right? So examples of a sub-ring, right? So one, 2z is a subset of z. Okay, 2z is a subset of z. So basically what this is trying to tell us is that 2z, of which we know that 2z is the set of all even integers. 2z is the set of all even integers. So let me write it. Is the set of all even integers, right? So with these even integers, we can talk about -4, -2, 0, 2, 4, to infinity, right? So these are all even integers. Even integers. Okay. With the z, we know that the z is the set of all integers, right? So we can have example like -1, 0, 1, to infinity. So we have all numbers in here except fractions or decimals. You know, integers doesn't allow fractions or decimals, right? So all numbers are allowed here, but in here we are allowing only even integers. Only even integers. So this inclusion clearly shows that 2z is a subset of z. So you can say that 2z is indeed a subset of z. Okay, so this is a perfect example for a subring. So 2z is a subset of z. Are we clear with that? So I can give you an illustration for this. Okay, an illustration for this. So you know that when you have your bigger, right? This is your bigger rectangle, right? Now let's have some small rectangle inside that. Okay, so inside the bigger rectangle or inside the larger rectangle is the 2z. Okay, and outside the smaller rectangle is the z. Okay, so we have that. So this means that this here is embedded in the bigger rectangle or the larger rectangle. So this clearly shows that 2z is a subset of z. 2z is a subset of z. Okay, so this inclusion clearly shows that 2z is a subring and is also an ideal of z. Very soon we'll move to the ideal and we know what the ideals are. Okay, so that is our conclusion to this example. 2z is a subring and it's also an ideal of z. Okay, so that is a perfect example for a subring. Let's look at the second example. The second example of which is z of x squared, this is under polynomial, right, is a subset of z of x. Okay, so this example looks more abstract, but I will try my best to use illustrations for it like this to explain this example. So this is our example 2. Okay, so this here means that 2z of x squared is defined based on some polynomial, right? Specific polynomial. This z of x squared is defined based on a particular polynomial, of which this is, right? We have, this is basically ring of all polynomials with integer coefficient. So this is ring of all polynomials with integer coefficient. Okay, then z of x squared is basically ring of polynomials with z of x squared. It is basically a subset of what? Z of x, and it consists of polynomials with s squared only. It consists of polynomials with s squared only. So this is a subset, or it's a subring, okay? It's a subring of z of x and consists of polynomial with s squared only. All right. So basically, we can say that z of x squared is a subring of z of x in here. So let me illustrate that in a diagram, right? So we have our z of x squared in here, and we have our z of x, okay? Right? So from this illustration, we can see clearly that z of x squared is basically embedded in the larger rectangle, and this is superseding this right now here, okay? This z of x is bigger than z of x squared, so this is a subring of this. Okay, for example, you can have an example for z of x squared as something like 3x squared, or let me start with 3x power 4 plus 2x squared plus say 7, right? Or x power 6 plus x power 4 plus 2x squared, etc. Right? All these are examples of this z of x squared. You can have example for z of x as z of x contains all of this, right? Z of x can contain all of this, but z of x squared cannot contain everything in z of x. So we can have something like x power 4, x power 3, plus x power 2 plus 1, and so forth and so on, right? So in here, we can not see anything like any power like x power 1 or x power 3 or x power 5. No, all the powers in here are even. All the power over here, all the powers in here are even. So this clearly shows that this is embedded in this. So this is a subring of this. Okay, so that is a perfect example for a subring. So I think these two examples are enough. We can proceed to ideals, right? That is amazing. Okay, so we move on. Ideals are, so that we move to the coset, and then we finally look at the quotient rings. Okay, so with the ideals, ideals are basically a subset of the ring. Okay, ideals are basically a subset. So ideals, an idol, say an idol denoted as I is a subset of R. So that is a subset, if A a subring, if it's a subring, B if it is an absorbing under multiplication, absorbing under multiplication. So within this, we can talk about so many things in here. Okay, within this, we can talk about so many things in here. We can talk about we can say that for all R that belongs to R, for all R that belongs to R, and also for all A that belongs to R, okay, for all A that belongs to I, and then AR that belongs to I, and RA that belongs to I, then we've defined what ideals are. So basically, the definition for ideal is a subset, and this subset is a subring, and it must be a subring, and it must be an absorbing under multiplication, of which for all values of R that belongs to R, okay, and for all values of A, or for all A that belongs to I, and AR belongs to I, and RA belongs to I. So I'll explain all these notations in here. Okay, so now we have to know the types of ideals. Okay, so we look at the types of ideals. So one, we have the right idol, okay, the right idol, of which it's denoted as AR. All right, AR. So that is the right idol. So AR belongs to I. You know, the idol is denoted as what? I. Okay, and the second idol is the left idol. okay? And that is RA. That also belongs to I. Then the final type of the idol is the two-sided idol. The two-sided idol. So we have the two-sided idol. Okay, that is when we have the left and the right together, both at a time. Okay, so this one is mostly common in the commutative rings. So in the quotient rings, this is what we will be using a lot. You'll be using the two-sided idol a lot. So take note of that. So we have the two-sided idol in here. So we have three types of idol. We have the left and the right. Then we have both left and right. And that is the two-sided idol. Okay, so look at some few examples of the idol. One, you have n. This n is a subset of z. Okay, this n is a subset of z, and basically it's an idol for any n that belongs to z. So it's an idol. It's an idol for any n that belongs to z. Okay. Second example is z x in here being a subset of what? Z. X in here is a subset of what? Z, right? And that is basically a subset of z of x, okay? And the polynomials, okay? So we have to look at that first, okay? So x is a subset of what? Z of x. So this is under integer under the polynomials, right? So that is all polynomials divisible by x. All polynomials divisible by x. So this is all polynomials divisible by x. Okay, so that is the second example under the ideals. I think these examples should be enough. Now let's look at some key properties under the ideal. Okay, so first of all, what you have to know is that ideals, right, generalizes the concept of divisibility. That is the first property that you have to know. Ideals generalizes the concept of divisibility. Okay, and the second property that you have to know is that every ideal in Z is a principal, or that is of the form N. So the key properties are: one, every ideal is a principal of Z. Two, ideals generalizes the concept of divisibility. So that is the key properties of ideals. Take note. Very, very important. So now we know the key properties of ideals. We have learned some few examples. We can now move on to what I want to explain what the absorbing basically means in the ideals. Okay, so let's look at this illustration. Let's look at this illustration. So for instance, you have some uh, plane. Let's say this surrounding is a plane, okay? And you have a ring in there and some elements, right? Now you have this here, you have R, you have this, right? So this is pointing downwards, right? So this is I. So, okay. Okay, so this is the illustration for the absorbing uh here. Okay, the absorbing in the ideal. So you see, you have the ring. There is an element together with what? The ring. Okay, and this R here is trying to pull this element in the ring towards itself. Okay, it's trying to pull this element towards itself. And when it pulls this element towards itself, it is going into the what? Idle, right? So this pulls this element to itself, and you have what? RE, right? You have RE. And that is basically the left idle, right? That is the left idle. And this element, very interesting. This here, right, also pulls this element to itself, right? So you have AR, right? And this is the left idle. So this pulls this element to itself, and you have AR, and it's entering the I, which is the idle. Okay, so AR to the element I, which forms the idle. So the idle pulls an element from the ring towards itself to form the idle. That is the basic understanding of the absorbing under multiplication. So, right, so this comes here, pulls it towards itself via multiplication. So it pulls this element towards itself via multiplication. So it comes here and it forms RA. It doesn't goes back again because it's multiplication. So it holds it here, and once it holds it here, you know the arrow is pointing downwards. And in here is what? Idle. So it pulls the element towards itself via multiplication, and it comes to form what? The left idle on this side, and it forms the right idle on this side. So that is the absorbing stage. That is the absorbing stage. Okay. So now we can move on to the cosets. Okay, we can move on to the coset. But before we move on to the coset, I want to give you some interesting and a practical example for the absorbing under multiplication. Okay, so you know what? Think of the idol, the eye, as a sponge. Okay, think of the eye as a sponge, your bathing sponge or your washing sponge, whatever sponge you know. Think of the eye as a sponge. Okay, so let's say you drop anything from uh, the R, you drop anything from the R into the I, which is the sponge. Okay, so let's say you are buffing, right? And you drop something, let's say anything, right? From R, you set up something from R into the I, which is the sponge, right? And this dropping that you are doing is under multiplication or via multiplication. And once you drop the something from the ring, which is the R, it stays there. It doesn't go back, right? It stays there. It doesn't go back. So that is the best example, or that is the illustration of the absorbing. Okay, so this coset concept is very simple. Okay, and this is how the definition goes. So let's say that for some element, say A, okay, and this element A belongs to the ring R, okay. This element A belongs to the ring R. Now this element A that belongs to R, and there is an idle, okay, which is often denoted as I. All right. Then we can say that the coset A plus I, the coset, A plus I is giving us A plus I complex slash I given I that belongs to what? I, right? So this I here could denote any number of what? I. So we can have I1, I2, I3. All these I's belongs to the bigger I. So I that belongs to what? I. So that is the basic definition for the coset. Okay. Now let me give you some illustration that that will define the cosets in a very simple way. Okay, so let's say you have this diagram. Okay, this is your, let's say this is your environment. This is a plane. Let's say this is a plane, right? And you divided or you partition this plane into sections, right? This is how you've partitioned this plane, okay? And you call here A plus I, you call here A plus B plus I, you call here C plus I, and you call here D plus I, right? This is a plane. The background is a plane of which the ring is located. Okay, so the ring is here, and you've partitioned it into sections. And these sections, every section, every region is in its own house. None crosses the other, right? So this is a coset, this is a coset, this is a coset, this is a coset, right? So coset basically means that the this ideal here, the ideal I, partitions are into disjoint cosets. All right, that is the illustration. I'm trying to explain the illustration on the board. And in the diagram that we have over here, we can see that the entire space, this entire space, all right, the entire space may be a plane. right? You can assume it to be a plane, okay? Or you can say a set of points that we join together. You know, it's a set of points that forms a circle, right? And we represent that as what they are, the rank. Okay. And we've divided it into sections. We've divided it into sections. These sections, none of them intersect. None of them intersect. Each represents what? A coset. So, like A plus I, B plus I, etc. Each represents a coset. So all these regions, this region is a coset, this region is a coset, this region is a coset, this region is a coset as well. You can divide it as many as you want, but make sure that none intersect, right? And that is what defines a coset. Okay, so that is the key idea of a partition. That is the basic idea of a partition. Okay, so let's look at some example to clarify the concept of coset. Okay, so this is the example that we are coming to talk about on the coset. Okay, so the coset over here are 1. The cosets are 1. 0 plus 3z, and that is equal to, this 3z basically means that you are in modulo what? 3, right? So anything that you do, has to be in mode 3, right? So we say that our first coset is 0 plus I, and that is equal to, 0 plus I under this problem, right? R equals Z and I is equal to 3Z. So I here is an idle, R here is a ring, and Z is integer, right? So 0 plus I is basically under the definition 0 from negative infinity to that of positive infinity, but we're going to have -6, right? -6, comma, -3, right? 0, comma, 3, 6, to infinity, right? And the second coset is 1 plus I, okay? And that is to infinity, right? So comma, -5, -2, 1, 4, 7 to infinity, right? Then we have the last one to be 2 plus I, and that is comma, -4, -1, 2, 5, 8 to infinity, right? So you can see that these are the cosets that we got from this example, right? So R equals Z and I equals 3Z. The cosets are 0 plus I, and the members in there are from negative infinity, right? So we're going to have -6, -3, comma, 0, comma, 3, 6, comma, to infinity, right? Then 1 plus I equals the element in there from negative infinity, then from here negative 5, comma, negative 2, comma, 1, comma, 4, comma, 7 to infinity. Then 2 plus I is from negative infinity. Then we start from negative 4, negative 1, 2, 5, 8. Okay, so that is for this example. Okay, that is for this example. So this is a coset, this is a coset, this is a coset. So that means that each coset will be in exactly one region, right? Each number will fall into exactly one of these cosets. Each number will fall into exactly one of these cosets. So you can put this here, you can put this here, you can put that there. Okay, so each number should fall in exactly one coset. They shouldn't intersect, they shouldn't meet, right? So that is the example for coset. The example for coset. Okay, so now we move on to the quotient rings itself, right? But before then, I want you to understand the reason why we divided these sections, right? Or why we studied this particular coset thing, right? So the reason for the division of this coset, right, into disjoint coset, right? The division into disjoint coset is what I mean, that is what forms the structure of a quotient ring. Okay, the division of these stuffs, okay, the division into disjoint coset is what forms the structure of a quotient ring. Okay, and the quotient ring is denoted as R slash R, R slash I. That is the quotient ring. So these divisions in here are what forms the structure of a quotient ring. So the elements of the quotient ring are uh, the cosets. They are the cosets, and basically under addition and multiplication. That is where, or that is how we talk about that. Addition and multiplication are done between cosets. Okay, so that is for it. Now let's look at the quotient rings. Okay, so first of all, we'll begin with the construction of a quotient ring. Okay, so before we go ahead with the construction and then move on to the properties, we have to look at what uh, is meant by quotient rings, right? So we look at quotient rings, right? So we look at what quotient rings are. So basically, when we talk about quotient rings are basically defined. You know, the reason why we studied the rings before we came to the we are coming to the quotient rings is because we are going to apply the concept in the rings in the uh, quotient rings as well. So the quotient ring is defined as, so let's say that we are giving something like giving um, giving a ring, R, and a two-sided idle. Okay, don't forget we studied the types of idle, and I made mention that we'll be using the two-sided a lot in the quotient rings, right? So given a ring R and a two-sided idle I, okay, a two-sided idle I, and that two-sided idle I is a subring or is a subset of the ring, okay? So the quotient ring, often denoted as R on I, is the set of cosets, of the form A plus I equals A plus I complex. You know, this I can be I1, I2, I3, and so forth, right? Good. So this is the definition for the quotient rings. And quotient rings are defined under two operations, right? Under addition and multiplication. As we know in rings as well, you know, rings are defined based on two operations, under addition and multiplication. In here too, they are defined under two operations, addition and multiplication. So let's look at, so each note, each element of R on I is a coset of the idle, I, is a coset of the idle I. Okay, so that is what you have to note about the quotient rings. Now, the quotient rings, you know, they are defined under two operations, and these are defined operations, right? The first one is addition. So we have addition, and under the addition, for instance, and you have A plus B, A plus I plus B plus I, then you have A plus B plus I. So when you combine two cosets, okay, you have the coset, the element of the coset plus an idle, all right? So that is the first definition. So the reason why we pick just one I is because the proof is there, and the proof is very simple. I just want to show you the operations that we are going to use so that we use it to solve problems, right? So this here, you know, we combine this and this and we use this, right? The reason is that this can be defined as I1, and this I1 belongs to what? I. This 2 can be defined as I2, and this I2 belongs to what? I. So if this belongs to I and this belongs to I, then we can say that I1 plus I2 belongs to what? I. So that is why we have only one I for the definition. Okay, let's look at the second operation, which is the multiplication. Okay, so with the multiplication, for instance, you have this coset a plus I times b plus I. You're going to have ab plus I. So with this as well is defined this way as well. So this I here can be I1, and this I1 belongs to I. This as well can be defined as I2, and that belongs to what? I. So this and this, they are all in I. So we choose one I, and then that is what we have there. Okay, so these are the operations for the quotient ring. These are the operations in the quotient ring. Okay, we have the proofs, but the proofs are not really tough to do or to go about. So I think you can go about that yourself. Now we look at the construction. Okay, so we look at the properties of a quotient ring, and they are just fundamental properties. Okay, I'll explain each property into details so that it will be very easy to move along with the quotient rings, right? So let's take the first property. So before we move on, let's say that R is a ring and I is an idle. Okay, R is a ring and I is an idle in the R. So in the R. Okay, now one, we are saying that R on I is a ring. That is what we are saying. So we've defined that R should be a ring and I should be an idle in R. So the first property is R on I is a ring in here. Okay, so this is what it basically means. You know, it inherits this R on I inherits some properties from the ring, right? So one, we know that it inherits it inherits it inherits the ring structure. It inherits the ring structure from R. Okay, that is under addition. Don't forget, in the ring, it is defined based on two binary operations, right? And in the quotient ring, it is also defined based on binary two operations, that is addition and multiplication. So it's, first of all, it inherits the ring structure from R, that is addition and multiplication. Okay, two, if R has a multiplication, if R has a multiplication, or if R has a multiplicative identity, if R has a multiplicative identity, which is 1, then R on I may or may not have 1, depending on whether 1 belongs to what? I. depending on whether 1 belongs to I. 1 here is the multiplicative identity. Okay, then, okay, so that is the first identity. If we've defined R as a ring, and we've defined I as an idle in the ring, which is R. And we are saying that R on I is a ring, right? So what we are saying is that this R on I inherits the ring structure from R, which is the ring. And these are addition and multiplication. 2. If R has a multiplicative identity 1, then R on I may or may not have 1, depending on whether 1 belongs to I. Okay, so my basic explanation to this property is that, you see, when R is a ring, when R is a ring and I is an idle, okay, and I is an idle in the ring R, then the quotient ring, which is R on I, is a new ring structure, or is a new ring that has been formed, or is a new ring made from the set of cosets. It's a new ring made from the set of cosets, right? And this coset, you know that you can have A plus I, you can have B plus I, you can have C plus I, and so forth. For the A, the B, the C, and many other elements can or belongs to the what? R, which is the ring. Okay. This ring, okay, this ring inherits addition and multiplication as stated in there from the ring, okay, from the ring R. And the operations are well defined under as associative and distributive. However, the existence of multiplicative identity, whether R on I has a 1, depends on whether the identity element 1R, 1 sub R, 1 sub R in ring lies in the idle. In the ring lies in the idle. Okay? In the ring lies in the idle. Okay? Then every element of R on I becomes 0. So R on I is the 0 ring. Okay? R on I is the 0 ring. So if R, this 1R, does not belong to I, okay, does not belong to I, then R on I may retain a new or may retain a non-zero identity depending on the structure of what? R. Depending on the structure of what? R and the I. Depending on the structure of what? R and the I. Okay, so this basically shows that the identity in R, doesn't automatically passes to R on I. Okay, the identity in R doesn't automatically passes to R on I. Okay, so that is the first property. Okay, so the second property is if R on I if R on I is a commutative ring, R on I is a commutative ring if and only if R on I is a commutative ring if and only if R is commutative. If and only if R is commutative, then so is R on I, because the multiplicative or the multiplication of cosets greater mirrors that of R. Okay, so that is the second property. Now let me explain this property. This property basically means that, the meaning of the commutative ring is basically a ring. So let's say a ring R, okay, is commutative if AB is equal to BA, okay? If AB is equal to BA for all A and B that belongs to what? R, okay? So for all A and B that belongs to what? R. So that is the commutativity, okay? That is the commutativity. So multiplication is or multiplication in the R, which is the ring, doesn't depend on the order. Multiplication in the ring doesn't depend on the order. Okay, so order is not respected in there. All right. So that is for this second property. The third property is that R on I is a field. R on I is a field if and only if I is a maximal. If and only if I is a maximal idle in R. Okay, so that is the third property. R on A, right? This R on I, which is the quotient ring, is a field if and only if I is a maximal idle in R, which is the ring. Okay, so this property, my basic explanation to this property is that a field, okay, a field is a commutative ring, right? A field is a commutative ring with 1 not equal to 0. So it's a commutative ring with 1 not equal to 0. 1 not equal to 0. That is, if a field is a commutative ring, 1 is not equal to 0. Okay? Where every non-zero element has a multiplicative what? Inverse. So a maximal ideal, which is the I, is in the rank R, is an ideal such that there is no other ideal, say J, okay, say J with I that is a subset or equal to, it shouldn't be equal to, but it's a subset. A subset I shouldn't be equal to, but it's a subset of J, and this is a subset, but it's not equal to the ring. Okay, it's not equal to the ring. Okay, so that is what you have to know. In other words, we can say that the only ideal containing I, the only ideal containing I are I and the whole ring R. The only ideal I containing R is the ideal, the whole ideal R. In other words, the only ideal containing I are I and the whole ring R. Okay. So that is for the third property line. Okay, so the fourth property is R on I is an integral domain. Is an integral domain if and only if I is a prime. If and only if I is a prime ideal. Okay, so that is the fourth property that you have to know. So take note of the various properties. The first property, the second property, and the third, the third and the fourth property. Okay, so we are going to take a problem to analyze these properties into details. Right. So we begin with problem 1. Okay, so the problem 1 says we should define what is meant by a quotient ring, which is R on I, where R is a ring and I is an ideal of R. Okay, so first of all, if we are asked this problem, what you have to know is that this is abstract, okay? And this is the second phase of abstract algebra, okay? So the first thing you have to do is to define your parameters, right? So you say that let R be the ring, right? R be the ring and I, which is a subset of R, be the ideal of R. Okay, so once you define these terms, then is the quotient ring is the quotient ring is the set of cosets, right? Is the set of cosets, right? R on I, the quotient ring is the set of cosets, right? And that is equal to we did it from the previous the introduction. That is equal to R plus I complex, right? R plus I, which is the ideal, right? Given that R belongs to what? Small r belongs to what? R. So you define your quotient ring this way, right? And note, each element is a coset of the form. Each element is a coset of the form R plus I equals R plus a complex I. You know, this complex I can be I1, I2, I3, I4, and so forth, right? And that is I. Okay, so once you define these terms, you are almost down the line. What you have to tell them is that the operations in R on I are defined as, you get the point, the operations in R on I are defined as one, addition, of which you know the addition is A plus I plus B plus I. This is a coset. This is also a coset, and this is giving us A plus B plus I, right? And 2, the multiplication. With the multiplication, you know that when you multiply 2 cosets, you have AB plus what? I. So these are the operations in R on I. That is it. So these are well defined because I is an idle. These are well defined because I is an idle. And that is the end of the problem. So we are asked to define uh, quotient ring, which is R on I. Okay, they define the terms for us. So what you need to do is redefine the terms with the same definitions. Then you tell them that R on I, which is the quotient ring, is the set of cosets. Is the set of what? Cosets. And that is defined this way. Then you go ahead to say that R plus I is equal to this here, right? You know, I can be I1, I2, I3, as I said. Then the operations in R on I are defined as addition, of which when you add 2 cosets, you have this. And under multiplication, when you multiply 2 cosets, you have this, period. So that is the end of the problem 1. Let's look at problem 2. Okay, so with problem 2, the question is R is equal to Z and I is equal to 6Z. Now the question goes ahead to ask, or it says we should describe the quotient ring Z on 6Z and state or say the kind of ring is it. Okay, so first of all, if you have a question of this kind, first thing you have to think of is that you know that Z on 6Z is basically ring of integer modulo 6, right? Ring of integer modulo 6, okay? That is ring of integer modulo 6, okay? So 6Z on 6Z is the ring of integer modulo 6. That is the first thing you have to state. 2, you know that Z on 6Z, you can define the element, right? So this is basically, you know, this is mode, right? And mode 6, you know the element involved. 0 bar, 1 bar, 2 bar, 3 bar, 4 bar, and 5 bar, right? So these are the elements involved in Z on 6Z, right? So this ring has basically 6 elements in it, right? It has 1, 2, 3, 4, 5, 6 elements in it. So this ring has 6 elements in it. It has 6 elements. And once it has 6 elements, first thing you have to know is that it is A. It is A. It is not, can you tell me? Once it has 6 elements, you have to know that it is not a field. The reason is because not all elements have a multiplicative inverse. So it is not a field because not all elements have a multiplicative what? Inverse. So it is not a field because not all elements have a multiplicative inverse. So we are still describing, right? B, it is not, can you tell me the next? The first one, because it has 6 elements, I will explain all these concepts once we are done with this problem. It's because it has 6 elements, it is not a field because not all elements have what? A multiplicative inverse. B, it is not an integral domain, okay? It is not an integral domain because it has a zero what? Divisor. It is not an integral domain because it has a zero divisor. And I'll give you an example. So it is not an integral domain because it has a zero divisors. Okay, so an example is, you know that 2 bar dot 3 bar is equal to what? 2 bar dot 3 bar is equal to what? 6 bar. And that is equal to what? 0 bar, right? So this makes it not to be what? An integral domain because it has a what? A zero divisor. Okay, so with this description, we can say that Z on 6Z, Z on 6Z is a finite commutative what? Ring. Okay? We are answering the second part of the question. For the description, that is what we've done. Any form of this question, this is how it goes. Okay? And I'll give you more details as to how you answer variety on this of these questions. Okay, so we are done with the description. So the other part, we can say that hence Z on 6Z is a finite commutative ring. Okay, Z on 6Z is a finite commutative ring with 0 what? Divisors. With 0 what? Divisors. Okay, with 0 divisors. So what kind of ring is it? That is what we've answered over here. It's a finite commutative ring with 0 divisors. So that is the solution to this particular problem. Okay, so let me give you some few tips so that any form that a question comes on this structure, you can answer it with ease. Okay, so note that every Z on NZ is a ring. Okay, so note that every Z on NZ is a ring. Okay, but what you have to know is that N should not be equal to -1 because um, it shouldn't have a negative n because you are talking about modulo, and modulo, we don't talk about negative numbers in modulo. Okay, so n should not be equal to a negative number. Okay, so Z on NZ is a ring no matter what n is, provided it is not a negative number, and it should be so the truth is, the fact is that it should be greater than 1 or equal to 1. If it is equal to 1, then it is a trivial ring. Okay, if it is equal to 1, then it is a trivial ring, right? So that is the first thing you have to know. Every Z on Z NZ is a ring. So every Z on NZ is a ring. Okay, every Z on NZ is a ring. No matter what um, no matter what n is. But note, n should be greater than or equal to 1. And if n is equal to 1, then we have a trivial ring. Then we have a trivial ring. Okay, so take note of that. But also, n should never be equal to a negative number. Okay, s should never be less than 1. It should never be less than 1 because n is, we are talking about modulo, and modulo, we don't accept negative numbers in there, right? So n should never be less than 1. So that is the first thing. Okay, the second tip is if n is prime, then it implies that it is a field. If n is prime, then it implies that it is a field and it has no zero divisors. It has no zero divisors. 3, if n is composite, then it implies that if n is composite, then it implies that it is still a ring. It is still a ring, but has a zero divisor. So not a field. Okay, if n is composite numbers, composite numbers, right? If it is a composite number, it is still a field. It is still a ring. Okay, but it has a 0 divisors, and so once it has a 0 divisors, it is not. In a nutshell, quotient rings quotient rings of integers are always rings. Quotient rings of integers are always rings. But as to whether it is this kind of ring or that kind of ring would depend on the property, whether it is a prime, whether it is a composite, or if n is equal to 1. So quotient ring with integer is always a ring. Quotient ring with integer is always a ring. So note that. Always look out for this. If n is prime, then it is a field. No 0 divisors. It is a field, but it has no 0 divisors. 3. If n is composite number, it is also a ring, but it has a 0 divisors, and so it has no field. It is not a field, right? And if n is equal to 1, then it means you have a trivial ring. Okay, it means you have a trivial ring. So that is about the problem 2. Some few tips under the problem 2. Now let me take you through the problem 3, where we are asked to prove that quotient ring is a ring. That is interesting, right? Because we have already dealt with all about quotient rings and rings, so you know how you should be able to prove that quotient ring is a ring. Okay, we should prove that quotient ring is a ring, and we are to show that the set of cosets in that is the quotient rings forms a ring under coset addition and multiplication. So I'll handle the first part, and I'll give this as this will be just your rehearsals. Okay, so I'll try to explain, then I'll leave it out. Okay, so first of all, to this problem, the demand is we have to explain, or we have to check the axioms of rings in brief. Okay, we have to check the axioms of rings in brief. Not just we are not to write everything. We have to make it in brief. Okay, so first of all, we have to talk about closure. Okay, so closure. Okay, with the closure, we have to, let's say we have a b that belongs to a and b that belongs to the ring. Okay, a and b that belongs to the ring. Okay, then we can say that when we add a plus b, it should be in the quotient ring. Are we okay? When we add a plus b, it should be in the what? The ring. So a plus b should be in the ring. Okay, so a plus I plus b plus I is equal to a plus b plus I. Okay, and that is basically in the quotient ring. So this belongs to what? The quotient ring. Okay, that is the addition aspect. When we go to the multiplicative aspect, then we can say that a plus I multiplied by b plus I is equal to ab plus I, and this as well should be in the quotient ring. Okay, So follow the definition very well. When you add two cosets, okay, when you add two cosets, it should be equal to the elements plus the idle. And that should be in what? The quotient ring. Are we okay with that? Now, when you multiply the same coset, a plus I plus times b plus I, you should have ab plus what? I. And this should belong to what? The quotient ring. Okay, so that is the closure aspect. And then when you talk about the associativity, you know that the associativity follows from the ring. It follows from the ring. So that one, there's no need to do a whole lot of proofs, right? So the associativity follows from what? The ring in R. Okay, it follows from the ring in R. So that is for the associativity. So the associativity follows from associative in R. Okay, then the third one is we can talk about the additive identity. Okay, so with the additive identity, we say that 0 plus I is equal to what? I plus 0, and that is equal to 0. And that is the 0 element, right? That is the 0 element. Then we talk about the additive inverse. So with that, we can say that minus into a plus I is equal to minus into a plus I. And that is okay. So the last part, which is the distributive laws, the distributive laws, you can say a plus say I times b plus I plus say an element c plus I is equal to a ab plus ac plus I. And this is the same as a into b plus c plus I, right? So that is the distributive law for this proof. So that is the proof for this particular problem. Hence, quotient ring is a ring. So don't forget the conclusion. Hence, quotient ring is a ring as proven. Done. That is the process. Very, very simple. So the thing is, abstract algebra is about practicing. Keep practicing, like practice a whole lot of problems, and it's going to be easy. Thank you very much for watching. I really appreciate your time. Please don't forget to subscribe, share with your mates, and I'll give you more updates. On to the next video. Please keep learning and stay inspired. Bye bye.